In this video, we are going to prove the fundamental theorem of calculus, or at least the first part. The fundamental theorem of calculus says that if f of x is continuous on the closed interval a, b, then the derivative of the function, the integral from a to x of f of t dt, is going to equal f of x. So let's go ahead and prove that. So the first thing I want to do is I want to go back to the definition of the derivative. So I'm going to set up a definition of the derivative just to make my life easier. I'm going to use a of x to denote the integral from a to x of f of t dt. Sometimes that will be a little easier. So by the derivative definition, we have that the derivative of this thing here, I'll just write the derivative of a of x, because that's, why we wrote that. That's going to be the limit as h goes to 0 of a of x plus h minus a of x over h. And what is a of x? Well, that's going to be the integral from a to x plus h. So we're doing a of x plus h first. That's going to be the integral from a to x plus h of f of t dt minus the integral from a to x of f of t dt. We're going to have all of that over h. Now you might remember from your properties of integrals that the integral from a to x of f of t dt, we didn't write it exactly like this, but we can. If I take that and add on the integral from x to x plus h, of f of t dt, that will get me the integral from a to x plus h of f of t dt. All I need to do is subtract this from both sides. And what I'm left with is that the integral from x to x plus h of f of t dt equals the integral from a to x plus h of f of t dt minus the integral from a to x of f of t dt. Which, hey, look, that's exactly what we have in the numerator here. So I can go ahead and rewrite this as the limit as h goes to 0 of the integral from x to x plus h of f of t dt over h. Okay, here's where we're going to use the mean value theorem for integrals. So, since f is continuous on the interval x to x plus h, there is some x, we'll call it x sub h, such that between those, we'll actually call it c sub h, just for fun. There's some c sub h in that interval such that by the mean value theorem for integrals, we have that f of ch times the length of our interval, well, the length of our interval is h, equals the integral from x to x plus h of f of t dt. And this is by the mean value theorem for integrals. So I can go ahead and replace the numerator now with the c sub h. Why do I have a little h down there? Well, for h is going to 0, and for each h, this interval looks a little bit different, so I'm going to need to choose a different c value for all of those. So This is actually going to be, I'm replacing it with f of ch times h divided by h. Hey, look, those h's cancel. And what I'm left with is the limit as h goes to 0 of f of ch. And now we're in the home stretch, but we have a couple properties of limits that we need to use to finalize this. One thing we know is since f is continuous, the limit as h goes to 0 of f of ch is the same as f of the limit as h goes to 0 of ch. And that's just the property that you can move a limit inside a continuous function. So let's go ahead and rewrite it there. Just ch. And to finish this off, we are going to use our favorite, the squeeze theorem, to take this limit as h goes to 0 of ch. Because what do we know about ch? Well, it's between x and x plus h, which means that the limit as h goes to 0 of x is less than or equal to the limit as h goes to 0 of ch, which is less than or equal to the limit as h goes to 0 of x plus h. I know that this first one, well, x doesn't depend on h at all, so that's just x. This one up here, that's going to be x plus 0 as h goes to 0, so that's x. So this limit in the middle is also x. And we get that this limit ends up just being f of x, which is exactly what we wanted to show. We show that the derivative of the integral function equals f of x. There you go. That's how you can prove the fundamental theorem of calculus. In the next video, we'll prove the second part of this, which is way faster.